Yeah. Sorry, I'm an idiot. So hopefully I'll be fired at the end of semester. Oh, it starts. Yeah. So apologies to everybody, and I'm an idiot. Yeah. So, and on the other hand, Vsevolod is just here. Usually you remind me to start the broadcast, and today. Pardon me? Okay. Anyway, I'm sorry. So, yeah. Yeah. Well, at least everything is on the blackboard. Yeah, and that's also true. So here, a lambda of q is some q analog of z. So it's q to the power size of lambda plus twice n of lambda b lambda of q inverse. But the actual meaning of this expression is that this is the cardinality of the automorphism group of m lambda. So remember, we had O module, the finite O module of type lambda. Okay, and then at the very beginning of this topic, we started with computing its automorphism group, and this was the answer. And also, you may view this answer the following way. We have the group GLN of FQ, and there we have unipotent, say, U. Well, that's a bad name. Sorry. Maybe O lambda, a unipotent element of Jordan type lambda. Okay. Then we have the centralizer in the group, in the Hebbian group GLN of Q of this element O lambda. Okay, this is a subgroup, and it has well, this group is the automorphisms of M lambda. So its order in particular is given by this thing. Okay. So I also have to say what is Y. So Y lambda of Q is Q it's Y theta, sorry. Y theta of Q is Q to the power negative size of theta, so that is N, Z theta of Q inverse. Okay. And finally, the second orthogonality relation rewrites as over there as the sum over all partitions of size lambda, a lambda of Q inverse Q theta lambda of Q Q sigma lambda of Q equals delta theta sigma Y theta of Q. Okay. And the identity x theta mu of t equals the sum over lambda chi lambda of w theta times the Kostka coefficient polynomial k lambda mu of t becomes, in terms of green functions, becomes q theta mu of q equals the sum over lambda chi lambda of w theta with modified Kostka polynomials, which we defined last time. The modified Kostka polynomial lambda mu of q is q to the power n of mu, usual Kostka polynomial of q inverse. Yes. Yes, it took us a couple of months. It is a whole Littlewood polynomial. So, well, that's it. But still, I want to say how these green functions appear in nature. For example, for the characters of GLN of Q, or else in geometry. So the big discovery of Tony Springer in the mid-70s was that, say, the green function Q for this column partition 1 mu of Q is the Poincare polynomial of the what is nowadays called Springer fiber. B mu. So well, I mentioned this a few times. Let me say it once again. We have the cotangent bundle to the flag variety of complete flags in n-dimensional vector space, say over complex numbers. And this is the collection of well, a flag and an nilpotent element, say A, from Cn to itself, such that it respects this flag, but even more than respects if I becomes smaller. So A is a fortiori nilpotent element. Okay. And now there is this Springer resolution map to the nilpotent cone, which just forgets the flag. Well, it's called mu. It's not because it's partitioned, but because it's the moment map from the point of view of symplectic geometry. You just had a lecture by Patev where he might mention moment maps. I mean, this is an archetypical example of a symplectic variety, and the group GLN acts on the flag variety, so hence on its cotangent bundle. It's a Hamiltonian action, so there is a moment map. There is a moment map to the dual Lie algebra of GLN, which is self-dual because of killing form, and it lands into the nilpotent cone inside GLN. Okay, so there is this. In particular, in here you have various nilpotent orbits. They are numbered by partitions, by Jordan normal forms. And inside one such orbit, O mu, you take an nilpotent element E, number mu. Again, it's not an elementary symmetric function, but an nilpotent element. And then this Springer fiber, by definition, is just the inverse image of this element. Okay, I'm sorry for the bad notation. There is mu here, mu there, but well, I could. Well, wait, let me replace one mu with lambda. It'll be better. Yeah, that's better. This mu cannot be replaced by anything. It's a proper name. Okay. So in other words, you fix an nilpotent element, and you consider all the flags that are respected by this nilpotent element. Well, this is a very important but very complicated and singular variety. For example, if this lambda happens to be n minus 1, 1, then B lambda happens to be a collection of projective lines like this. And there are n minus 1 lines, and they intersect along this pattern. Okay, this can be generalized. I mean, I only said what is the geometric meaning of the green function Q column partition and arbitrary partition. Yeah, like this. And you can also consider an arbitrary pair of partitions. And then the corresponding green function also has some geometric meaning. So, more generally, Springer constructed the SN action in the cohomology of the Springer fiber like this. I mean, when I say Poincare polynomial, I mean they are dimensions of cohomology of this thing, yeah? And they, as you can see from this picture, they have partitions into cells, yeah? So you say this point is infinity, and you remove it, and what remains is the affine line here, which is one-dimensional cell. Then you take, then you call this point infinity again, you remove it, and what remains is another affine line, and so on. So you get cell partition of this thing, and any Springer fiber has a cell partition, which is a very, very non-trivial result, maybe not quite proved even to the date. Maybe in E8 type of special exceptional group, it is not yet fully proved. But for arbitrary Lie group, it's arbitrary Springer fiber has cell partition, is a union of cells over complex numbers. I think it's not quite yet fully proved for E8. Okay. So I mean, it follows that the cohomology only live in even degrees. And when I say Poincare polynomial, then this variable Q has degree 2. So there is an action like here. And we write Q theta lambda of Q is the sum of certain coefficients say C whatever theta lambda I. Maybe let me write this way. Lambda I of theta qi. Okay, there's a weird way to index the coefficients of this polynomial. It's a polynomial in Q, and its coefficients are indexed this weird way. Then this C lambda I of theta may be viewed. Yes. Well, so this is a polynomial in Q. So it has coefficients indexed by positive integers or non-negative integers. Well, these are here are those coefficients. But this is a weird way to index them. They depend on two partitions and on integer. Well, here are three guys, two partitions, and an integer. And this is a weird way to group them. Why do I group them this way? Here, I explain. Because this may be viewed as a central function on Sn as depending on this cycle type theta. And then C lambda I of theta is minus 1 to the power W trace of W inverse in the 2ith cohomology of the Springer fiber. Sorry, lambda. Oh, theta is in the, it indexes the conjugacy classes in the symmetric group. So that's why I grouped my parameters this way, so I can view this function as a central function depending on theta in the symmetric group. Okay. Well, if you believe this, then well, it follows that the green functions are the Frobenius trace functions of the character sheaves on GLN of FQ bar at the points at the unipotent elements. And well, in this particular case, it's the same as the character, the unipotent character values of GL and FQ at unipotent elements. Okay. And this has certain generalization for arbitrary Chevalier groups in place of GLN. But then for arbitrary groups, there's only one half of the story, because you do obtain this way. Well, I mean, there is generalization of the notion of green functions, and they're computable similarly, effectively computable. And they do give you the Frobenius trace functions of Carter sheaves, but they are not quite the Carter values of finite groups. You need to perform certain non-abelian Fourier transform discovered by Lustig to obtain from here the Carter values. But for GLN, the abelian Fourier transform is just trivial identity, and there is nothing else to do. You immediately obtain the Carter values. So that's the end of the story about whole little polynomials, and we move on to the further deformation, QQ deformation. But before we do this, let me try to answer the question Ira proposed last time, namely, why the hell are we interested in Macdonald polynomials? And it's not that I can answer this question, but let me say what it is related to. Because, well, say for me, most fascinating things in mathematics are relations between different areas. Like, for example, if you consider the Riemann sphere P1, then you know that any regular function, let's say holomorphic or algebraic, is constant because of the maximum principle, yeah, in complex analysis. On the other hand, from the point of view of algebraic geometry, any regular function on projective variety is also constant. And these are two different, absolutely different arguments. But they prove, so you can prove the same thing in two different ways. And this is most appealing and convincing. Then you know that this must be true, if you can prove it in two different ways. Like, for example, perhaps you know this story about Kolmogorov, that everybody does? That initially he was a historian. He studied, how's it called, paleography, yeah? Новгородские грамоты берестяны. I don't know how to say it in English. And at some point, he switched to mathematics because he explained that his advisor told him that in history, to convince somebody, you need to produce at least 5 different proofs, and mathematics just one suffices. But still, this historian point of view does make some sense. If you have more than one proof, it's more convincing, huh? Yeah, that's true. In history, true. Yeah. But even if I have two different proofs, both correct in mathematics, it's much more convincing. So there are some, well, different areas of mathematics where Macdonald polynomials appear. But that's not quite honest, because the area of mathematics I'm going to tell about just directly was born from Macdonald polynomials. So it's not independent, but still. So I mentioned already that if you're interested in representations of GL and FQ over complex numbers that have non-trivial invariance with respect to the upper triangular Borel subgroup, then the classification of such representations, they're called unipotent. I just mentioned them. Is the same as representations of the convolution algebra of the functions on GL and FQ, invariant both on the left and on the right with respect to the Borel subgroup. And this is called HQ, the Ivahori-Hecker algebra. Pardon me? VB? Invariance. Well, there is a Borel subgroup here, so it acts on V, and when anything acts on V, this superscript means invariance. So there's a lot of representations, and only a few of them, they're also indexed by partitions, have this property, unipotent ones. But somehow they're most important. We just saw that their characters are governed by green functions, and it turns out that the characters of everything else are also boiled down to green functions. Yes. So in other words, you can take the induction from Borel to GL and FQ of the trivial representation, and it's as the direct sum over all partitions. The corresponding representation unipotency U lambda, tensor multiplicity space, and this multiplicity space turns out to be, well, isomorphic to the irreducible representation of symmetric group. But in fact, here it rather appears in different incarnation. It's an irreducible representation of this Ivahori-Hecker algebra. But Ivahori-Hecker algebra, as I mentioned already, is abstractly isomorphic to the group algebra of symmetric group. Yes. Pardon me? But they are all conjugates, so it doesn't matter at all. Yes. All Borel subgroups are conjugate, yeah. Oh, yes. Well, maybe it's a matter of definition, but yes. Well, one of the definitions is Borel is a stabilizer of a flag, but certainly all the flags are conjugate. Okay, so you know that, say, Sn is a Coxeter group. So it has generators S1 and so on, Sn minus 1, and relations that Si squared is 1, and Si is I plus 1, Si is I plus 1, Si is I plus 1 is called Brady relation. And similarly, HQ is generated by Ti, well, T1 and so on, T and minus 1. And relations are just the same. Ti plus 1, Ti equals Ti plus 1, Ti plus 1. The Brady relation, just the same. And this one gets deformed. Ti minus Q, Ti plus 1 is 0. Okay. So you see that HQ deforms the group algebra of the symmetric group, but in fact this deformation along the positive real axis is trivial. That's why I write here, and that's why we can number the multiplicity spaces by the index multiplicity spaces by the irreducible representations of symmetric group. So this is fine. And now we can consider, say, p-adic group. GL and say QP, or maybe GL and the formal power series, formal Laurent series over FQ, something like this. And again, it has an analog of Borel subgroup. It's called Ivahori subgroup. And it's the same Ivahori, and it's the reason why this algebra is called Ivahori algebra. So now this group is infinite, but it's a topological group. It's locally compact because the field, the ground field, is locally compact, and it has maximal compact subgroup. Say K equals GL and ZP, or GL and formal power series. And then you see that for matrices in here, it makes sense, especially in here, it makes sense to take the value at t equals 0. And here, so to say, at p equals 0. Anyway, there is a projection from K to GL and FP, or maybe here, in the second case, to GL and FQ. Just evaluation at 0. And the Ivahori subgroup is well, let's call it evaluation. Is the inverse image of the Borel subgroup in GLN of Q. So there are matrices with integral coefficients such that they are divisible by p below diagonal. What's the question? Well, from here you take a reduction modulo p and get. Well, if it's ZP, yes, or I could take more general p-adic numbers, some finite extension, then I would have the residue field FQ. So this is the Ivahori subgroup, and it plays the role of this Borel subgroup in the infinite dimensional loop situation, so to say. And in particular, again, we can consider the endomorphisms over GL and, well, let me call this, I cannot stand. Calligraphic K. GL and K over the induced representation from the Ivahori subgroup to GL and K of trivial. This is called the affine Ivahori Haker algebra. And it is, again, presented via generators and relations, very, very similar to those. Namely, those relations are governed by the Dynkin graph. Yeah, we start with 1, 2, and so on, n minus 1, n minus 2. Okay, and if there is an edge, you have such a relation. If there is no edge, they just commute. And I didn't even write this down. Maybe I should write the far away generators commute. I should have written it, but I neglected. And here you just do absolutely the same thing. You only add one more vertex. So again, you have 1, 2, n minus 2, n minus 1, and you add 0 vertex, and you connect it to the extremal vertices there. So what you obtain is just a cycle. So this Dynkin diagram is called A n minus 1, and this Dynkin diagram is called A n minus 1 affine. Okay, and the relation is just the same. So you have one more T0, and this one more generator T0, and say T0, T1, T0 is T1, T0, T1, and T0, T n minus 1, T0 is T n minus 1, T0, T n minus 1. And again, T0 minus Q, T0 plus 1 is 0. Okay? This is a deformation. Now I'm starting to lie. So maybe let me add some disclaimer. This is almost a deformation of the affine Weil group. That is the affine symmetric group. S and affine. So these are permutations of the whole set of integers, not just from 1 to n, but the whole integral line, such that sigma of I plus n is sigma of I plus n. Okay, and this is false as stated. In order to, here I might take no deformation. So I might write T0 squared equals 1, or say S0 squared equals 1, like it was for the usual symmetric group. Okay, then it would define a group, a Coxeter group, but this would be a affine Coxeter group, infinite Coxeter group. Okay, and this algebra, and this, I want to say, I would like to say that this infinite Coxeter group given by non-deformed generators and relations is just this group of, so to say, n-periodic permutations. And this is not quite true. To be literally true, I need to impose certain relation that, certain normalization that, say, the sum of sigma of 1, sigma of I from 0 to n minus 1 is n minus 1 over 2. So if I impose this extra relation, then it's literally true. If I don't, then this group is a little bit bigger than this affine Coxeter group. But it doesn't matter much. Yes? And so what? I mean, if I know those guys, then everything else is determined by this relation. But those are absolutely arbitrary in principle. If I don't impose this relation, I can choose those values. I mean, they must represent all the residues modulo n, but otherwise they're absolutely arbitrary. Yeah? But if I impose this extra relation, then I do get literally such a Coxeter group. But it doesn't really matter for what I want to say. Pardon me? Well, I think that this is contained in McDonald's book in some other chapter, which we don't follow, but it is in there. Yeah, certainly, yeah. It's related to Brouillard or Iwasawa decomposition. Yeah, it's Brouillard decomposition of the affine group, yeah, of this loop group, GLN of K. Okay, so I want to say that from this presentation, it follows that this sigma Sn affine is isomorphic to the usual symmetric group Sn, semi-direct product with certain lattice. Z to the n. Yeah, because as I said, you must permute the residues modulo n, and apart from this, you can shift arbitrarily. Yeah, so there's permutation of residues and arbitrary shifts.
Sigma n affine,
Such permutations, n periodic permutations. Well, if you impose this relation, it would be z to the n minus 1. Okay. And similarly, it's called Joseph Bernstein presentation. The affine Iwahori-Heiker algebra is the semi-direct product of the finite Iwahori-Heiker algebra and just the polynomial ring, well, Z of well, maybe x1, xn. Okay, and again, if you want it in this presentation, then I want less parameters. Well, maybe. Okay, let me really impose this relation, sorry. Plus this relation. Here, and then I will have n minus 1, and then I will have n minus 1 here. And then it will be true as stated. Absolutely correct remark. It is similar, again, philosophically similar to the fact that, say, the Lie algebra, GL, or maybe SLN, I don't know, SLN, SLN of any field, say C of T, is simultaneously Katz-Moody algebra with the Dynkin diagram, as I said, affinization of this cyclic quiver. Yeah, so on the one hand, you see it is loop algebra, so you just take usual SLN, but you extend scalars of your field. Yeah, so it's loop algebra. On the other hand, it can be generated, well, presented by generators and relations, very similar to the usual one. You just add one more generator, if you have heard of anything like this. No. Chevalier generators, no? SER, EIFIHI. Okay, anyway, there is such a presentation. And now you can do the same thing once again. So I can consider what is called Cherednik, Ivan Cherednik, double affine Haker algebra. Or maybe I should place Cherednik in between. Double affine Cherednik Haker algebra. So Ivahori is replaced by Cherednik. And what you get is Dacha. Double affine Cherednik Haker algebra. Dacha, yeah. So you start with this Dynkin diagram. Okay, and you take the corresponding H Q affine given by generators and relations, and then you take its semi-direct product with Laurent polynomials in x1 and so on, xn. So to each vertex here, you assign one variable, and I didn't specify this action, this representation, but well, there is a way to define it via de Mazur operators, and then just literally the same construction gives you this. And this is called the double affine Haker algebra. It is how is it called? Something like this. Yes, double Haker Q. Okay, and now, pardon me? Yes. And now, last time I announced the McDonald polynomials as the eigenfunctions of a difference operator. Yeah, maybe from this point of view, this notation sucks. Maybe let me revise it before it's too late. Difference operators. These D and these D, well, there are n-1 here and there, but it's the very similar representation of some Ivahori-Haker algebra in some Laurent polynomial space. So difference of operators, well, maybe there was just one operator. As a difference operator in well, some symmetric functions of certain variables like this. Okay, so it turns out that in fact there are n many commuting difference operators d1 and so on dn and those x's are just our usual variables in polynomials. So the picture I presented last time is just a part of representation of a double affine Hecke algebra. So together with x's, they generate the so-called polynomial representation of the double affine Hecke algebra and somehow this was the discovery of Cherednik. Trying to understand this Macdonald polynomial business, he discovered this double affine Hecke algebra. And it was like 30 years ago, and since then it became ubiquitous. Whatever. Say, lately it's very popular in the business of knot invariance. Yeah, like Alexander polynomial or something, John's polynomial, whatever. And then it can be quantized or deformed, so it depends on not on one variable, but on three variables. And there are many generalizations of this, and they all come from Cherednik double affine Hecke algebra. At least there is a way to produce them from Cherednik Hecke algebra. Well, then it turned out that this algebra has is sort of elliptic object in nature, and it has trigonometric and rational degenerations. I mean, this algebra has trigonometric and rational degenerations, and they are also very useful in various areas of mathematics, in, say, integrable systems. Very many integrable systems arise from this. So, врождение. Yeah, yeah. At the base of things, yeah, elliptic curve can be can degenerate into projective line with double point, or even further into cusp singularity. So this is called multiplicative. This is called additive. But at the level of formulas, you either have formulas with theta functions, or the formulas with exponentials, or sines and cosines, or the rational functions, and they are well, probably. Well, you might have seen like expressions like theta of whatever x minus y over theta of I don't know what. What should I put here? I don't know. Maybe I shouldn't put anything in the numerator. X minus y, and then 1 over y1 minus x over y, or 1 minus x minus y. No? Say, Pyatov and Saponov, they're very fond of, say, R matrices which have something like this, or something like that. But there are elliptic R matrices which have something like this. Okay. So that's it. And, well, we only have 5 minutes left. I don't know. So maybe I should rather stop here. And next time we'll start slowly McDonald polynomials. So we'll deform everything with Q, starting with the scalar product, the whole Littlewood scalar product. We'll introduce Q in there. Yes. That's also true, yeah. But Kalezin probably had in mind this rational degeneration. It's true for them, yeah. Because this is related to, well, in this rational degeneration, we start with the group algebra of a symmetric group that acts on polynomials in and variables, and also, acts on polynomials in the dual space, like this. And those two also commute in some specific way. They do not commute with each other. They have specific commutation rules. And then you can deform this. You can introduce one more parameter, say kappa, here. And then indeed this will be the only. Maybe you should say it this way. You can take just the differential operators in n variables, so differential operators on Cn. This is exactly the deformation of a direct product of this and that, which I need. And you can take now the symmetric algebra of Sn acting naturally here. Okay. Then this allows a unique deformation with parameter kappa. And this is the rational Cherednik algebra of type A. Rational Cherednik algebra, yes, most degenerate. Mm-hmm. But then you see that it depends on the action of a Coxeter group here on this space. So this can be generalized to arbitrary, maybe not quite this space, but say on the cotangent space of that. And then given any reflection representation of a Coxeter group, or even reflection group, any reflection group with its reflection representation, you can form a similar object, similar deformation. Yeah. So many things are related to each other, but you have to somehow to learn them in arbitrary order, and then you'll be happy that they are related. But you have to start with something, and I propose to start with McDonald polynomials. That's what we'll do next time. Thank you.